welcome to my talk after that FaceTime interruption on reacting to the future of application architecture. So my name is Grace Jansen, and I'm a developer advocate at IBM. And IBM, I hope you guys have noticed from my shirt, there's a running theme here. And I turned from a developer advocate. I joined a year and a half ago, but before that, I was a biologist. So I'm hoping that through my biology, I can kind of help you guys to gain an understanding of what reactive application architecture is and why I think it's the future of application architecture. So to look forward to the future of application architecture, we first have to look back as to where we come from. So seeing as you guys are all at DevOps UK, I'm kind of assuming you already know this, so I'll skip through it real quick. So we started off with this sort of monolithic application where we had huge applications, and that was fine at the start when applications were small and we didn't have that many functions and we were able to deploy them easily. But as we gained more and more functionality and we improved our computing power, those applications grew to exponential sizes, and having monolithic application architecture just wasn't feasible anymore. So we moved to microservice architecture, which was a fantastic step forward. That allowed us to distribute out the different services, easily add features, find out where the bugs were, and easily replace them if we wanted to update. But this has caused new problems, and users nowadays have more demands than this. They don't just expect to be able to use a website or an order. If I use a website, I expect my application to never fail. Nowadays, users have these increased expectations, and the microservice application we use nowadays just doesn't quite reach those expectations or match what the user experience they're expecting is. So how do we tackle these new demands? How do we tackle the demands of, if I'm using Amazon and I put something into my shopping trolley, I don't expect that item to disappear before I've checked out. I also don't expect to go onto Facebook and find that I can't use Messenger. Nowadays, I expect my applications to be resilient and responsive to my clicks, to my usage, to everything I'm doing on them. So how do we go forward in our evolution from microservices to try and achieve these behaviors that we want? That's where bees come in. So it might not be obvious at first. I promise it will be later. So bees are an amazing social. They have an amazing social structure, and they actually have a lot of the behaviors that we want to see in our microservices and in our application architecture. Which I'll show you through 3 examples of their behavior. So, first example I'm going to show is food foraging. So, when bees forage for food, they have this dance pattern. So they have these designated dance floors inside the beehive where forager bees will go out and look for food, and when they find food, they'll come back to the beehive, make their way onto the dance floor, wiggle their bottoms about a bit to show the other bees where the food is. And they have this amazing, incredible ability to narrow down that precise location so they can tell the other bees, that are the observer bees around the outside, they can tell them where the plant is, how rich the food source is. They can even account for wind factor when trying to reach that food source, all through the communication of dance. And so they are incredibly great at being able to communicate that to the observer bees. Now, what's important for a bee is that flower doesn't last forever. There are tons of other beehives out there that could have found that flower in the same time. So what's really important is that these observer bees down the bottom respond as soon as possible to get to that food source, because they want to get there before any other beehive does. So they have to quickly get the information that they need. They never stay for longer than they need to. As soon as they've got that basic information, like location of the flower, how rich it is, and where they need to go to get it, and whether they're needed, they head off immediately. They're extremely responsive in that way. And we want our applications to be the same. We want our applications to be as responsive as we can get them to be. So the second behavior I'm going to show is what happens when the queen dies. So for those of you who don't know much about bee societies, the queen bee is the be-all and end-all, pun intended. So the queen bee is like the most essential member of that beehive community. Without the queen bee, there's no more newbies and the beehive can't continue. So what happens when this essential member of the system disappears, either through death or that she's dying and they need to replace her? Well, bees are amazingly resilient in the fact that they're able to undertake a series of steps to know when the queen is dying or dead. So the queen produces these pheromone signals. So the main ways bees communicate are through dance, like I showed in the last slide, and through pheromone signals, so chemical signals that they emit from their body. And the queen emits this specific pheromone signal that all of the other bees in the hive can pick up on, but when the queen dies or is dying, that pheromone signal decreases or eventually disappears. So there's certain bees, nurser bees, around the hive that are able to pick up on this pheromone change. And when they pick up on this change, they're able to set in motion a series of steps to nominate a new queen. So what they do is they go into the hive and they find some larvae that haven't been born yet of new bees, and they feed them royal jelly. And what this royal jelly does is turn them into a queen bee. So when the first queen bee pops out, she brutally kills the other queen bees, as is necessary, and then becomes the queen. Unfortunately. I mean, we don't want the brutality in our services, but we certainly want the resiliency. So despite the fact that this whole process can take up to a month to happen, but considering how fast and how long beehives tend to last for, this is actually pretty damn quick. So they're able to put in motion these steps, and in the meantime, the rest of the hive is able to continue. So they don't collapse, they don't break down, they don't fail as a hive, they don't stop working because the most important member of their hive died. They just respond to it and react to it in a way that means that they can replace it as soon and as quickly as possible, which is exactly what we want from our systems and from our applications. If one of my most important microservices goes down, I don't want my whole application crashing because of that. I want it responding and reacting and replacing it as soon as it can. So they're extremely great at being resilient. What about the third situation? So this is the last one. So what happens when the hive is at war? So let's imagine that something bigger than this worm is coming at the hive. Let's imagine it's a big grizzly bear. One bee is not going to be enough to tackle that bear. So normally in bees, it's only about 12% of the hive take on the role of a guard bee. It's one of the many roles that bees tend to play in the hive. Now these guard bees are in charge of protecting the hive from such threats. But when something like a bear comes along, 10% of the hive just isn't going to cut it. So what bees are able to do is they're able to detect that this threat is more than they can handle. It's a bigger load that they're able to cope with. So instead they go back into the hive and they recruit other bees. So there are tons of different bee roles. Some of them are nurser bees, some are undertaker bees, some are even air conditioning bees to circulate air through the hive. So there's tons of different roles, and they go into the hive and they pick the bees that are kind of nearest to the doorways and signal to them, look, we need to recruit you as temporary guards. So out come the new guard bees temporarily as guards for the increased load of whatever's attacking their hive. So bees are amazing at being able to be elastic in their role switching, and they're able to switch depending on the load that is imposed on that system. And again, that's exactly what we want from applications. We want our applications to be able to deal with increased load. If I've got a new phone release, for example, on a website, I don't want it crashing just because I've got 100 new users. I want to be able to respond to that in a way that's is as cost efficient as possible. I don't want to have to buy a ton more cloud services just so that in the emergency that I have these 100 new users. I want my system responding and being as elastic as possible. So I'm going to try and relate this back to software now. So how does this all relate? Has anyone here ever heard of the Reactive manifesto? Fab, a few hands. Great. So this won't be news to you. So I don't know if you've noticed the keywords I've been popping into the behaviors so far, but the Reactive manifesto was written in 2013 by a group of people kind of led by Jonas Bonner to collaborate and sort of solidify what the core principles were for building reactive applications. So if you can see here, I put the different behaviors up for each cornerstone of the Reactive manifesto. So the first one there is the dancer behavior that I told you about. So here, the bees have to be extremely responsive to get to that food source, that plant, as soon as possible. And again, that's exactly what we want in reactive applications. We want, when a user clicks a button, I want a response. I don't want to be sat there waiting, thinking, did I click that? Did that double click? Did that work? My users need to know when when the system is responding to something that they've done. The next one is, if you have a look, is the guard bees that I talked about, the last example. So we want our applications to be elastic, just like the bees were. We want them to be able to respond to that increased load in an elastic way. We also want, so the last example that I showed was the queen bee dying. That shows that the bees are extremely resilient. They don't shut down when the hive doesn't shut down, it doesn't stop existing, it doesn't stop working. They just get on with it and replace that queen. And that's exactly what we want from our microservices. But how do we achieve these cornerstones? Well, they're all underpinned by one common factor, which is common throughout all of the examples of the bees that I showed. And that's having message-driven communication. So in all of the communication I showed, there's either a one-to-one or a many-to-one or a one-to-many form of communication where they're passing messages. That message could be, hey, look, guys, there's a food source over here. Or, guys, we're under attack. I need more guard bees. Each of those is messages. And by using a message-driven form of communication, we can stop blocking and we can have a more asynchronous form of communication. So these are the cornerstones of the Reactive manifesto. And so we need all of these to be able to have a reactive application. So why do I think this means that reactive application is the future of application architecture? Well, all of those behaviors seem to solve the issues we've got with current application architecture. Currently, we're not as resilient and responsive as we need to be. So considering that this solves all the behaviors that we want, seems like a pretty straightforward answer to what we're looking for. Now, some of you may have heard of reactive programming rather than reactive applications. Has anyone been following the Championship League? I know we had it on at the speaker dinner. Yeah, Tottenham, and yeah, perfect. So we're going to use a football example here, so I'm hoping you all get this. In America, it sometimes gets lost. So if you imagine reactive programming as a team of individually amazing players, let's say we've got a team of Lionel Messis, and they are incredibly talented individuals, but they've never ever trained together. So even though they may be amazing at scoring or amazing at being able to respond to the ball being passed to them, they're able to tackle it up the field well, they aren't able to implicitly trust each other and know what the other one is going to do. That's reactive programming. Individually, it's amazing at being reactive, but as a system as a whole, it's not the complete package. They're going to lose to a team that's played together for 20 plus years, knows exactly what the other ones are going to do. They may not individually be as good a player, but they know how to work as a team well, and they're able to trust each other and be able to put into set plays that means that they can be responsive and reactive and resilient as a team. Now imagine both of those combined, a team of Lionel Messis that have played together for 20 years. You've got the dream team. So what we want to do with reactive application architecture is base it on reactive programming, but do it at the application level. So you want both of those to have a fully reactive application. So it's not just one that you need. So how does reactive architecture achieve this behavior? I hope you guys appreciate the pun. Couldn't resist. So how does it achieve the behavior that I talked about in the Reactive manifesto? How do we get there? I'm going to take you through some of the architectural tools that we use to be able to achieve this. So the first of those is domain-driven design, so DDD as we often call it. Anyone heard of DDB before? Just so I get an idea. Fabulous. Most of you in the room, so this won't be too difficult. So DDD, if you break that down into the different parts, you're looking at a domain. So a domain is basically just a sphere of knowledge or activity. So in this case, we're looking at a specific subject area on which the application is intended to apply. And driven design just means that we're driving the design of our application based on those domains, based on those specific subject areas. So it's a development approach less than a physical tool. So this aims to ease the creation of complex applications by dividing the system up into more bounded contexts. So in that way, we're able to split them up depending on what services they offer. And the way we do that is usually by identifying aggregate routes. So in the case of our bee example, we've got the overall example of a baby bee. That baby bee can become one of three things. It can either become a queen bee on the left here, or it can either become a drone bee on the right, or it become a worker bee. So all of the female bees are worker bees, male bees are drone bees, and there's only one queen ever in a hive. So each of those has a specific role, and it can't do what the other can do. So a drone can do what a worker does, a worker can't do what the queen does, and the queen can't do what any of the other two do. And that's exactly what we do with our microservices when we break them down. We look at what each can do to break them into the aggregate routes to find those bounded contexts. So we're able to split the workers, for example, into different jobs, but they all stem from the same aggregate root, which is the generic worker bee. And each of those, they're able to communicate efficiently by using a ubiquitous language between the two. So they're all able to use the same language to understand each other. But that's not the only issue. Within each bounded context, that ubiquitous language is great, but what about between microservices? Well, we want to use asynchronous communication, like I was talking about before. So to use the bee example again, imagine a beehive where you have to wait for a bee to come out before you get in. A bit like the speaker dinner was towards the end of the night last night, the after party. So imagine that you have to wait for that bee. You've got a line of bees waiting to deliver their honey. Those bees are wasted resources. They could be out there finding more honey, more pollen. They could be doing more jobs within the hive, and yet they have to wait because they've got a one in, one out system. That's not asynchronous communication. That's a blocking communication. And that means that we waste resources. So by having asynchronous communication, we're able to unblock those resources. And we're able to, so bees do this already, but they're able to just go in and out whenever they please. That's exactly what we want from microservices. We want those messages to be delivered as soon as possible instead of being blocked by something else in the system. So asynchronous communication is far more cost efficient, and it's far more efficient of the use of resources. But why is blocking so bad? Well, because you get this issue of wasted resources. So the need for asynchronous passing is a big one, and that's why it's the cornerstone of the Reactive manifesto. So why is this the cornerstone of the Reactive manifesto, especially in today's day and age? Well, we've moved from a data at rest sort of society to a data in motion. So way back when we had monolithic applications, it was fine to do batch processing, for example. So you'd give them the data, they'd batch process it, might take overnight, might take a long time. That's fine, there's not that much data. It won't have changed that much overnight, and you can process it that way. Nowadays, we need to be moving with the data in motion. So we don't have this data at rest anymore. So we had this sort of in-between stage where we started to use things like lambdas to try and have a bit of both. And now we want to move into the event streaming and event sourcing side of things and the event logging. So we want to fully embrace this data in motion. So that's another tool that we use in the reactive application architecture. So event sourcing and CQRS. So event sourcing, for those who haven't heard of it before, basically ensures that instead of just storing the data, you store state changes to the application. So if the application state changes, you store that state change rather than the data itself. So it stores it as a sequence of events. CQRS, on the other hand, CQRS stands for Command Query Responsibility Segregation. So that basically means that you're disassociating the write and the read of your system. So instead of having them in the same database, you have a write database and a read database, which means you can have higher availability. So linking it back to the bees already do this, we just don't realize. If you imagine each of the observer bees' brains is a read database and the dancer is writing to them on the dance floor, they each have their own local copy of that data. So when they fly away to the plant, they can access that data. So let's say a gust of wind comes along and brushes the bee off path. That bee can go back to the data and think, right, where was that plant again? Where do I need to go? I've got the data because it's in my brain already. So it means that they don't have to fly all the way back to the hive to find out where that plant was just to go back. But this means that we have high availability of the data, but it's not always consistent. So we have this high availability eventual consistency. It's part of the CAP theorem for those who haven't seen it. So with applications, we tend to have this sort of issue where we don't always have eventual consistency. We're not always up to date because we've got these separate read and writes. So let's look at the dance floor again. Let's say, for example, that food source that we found earlier that morning has run out of pollen. There's no point sending bees there anymore. So instead, the last bee who looked at the pollen and thought, that's run out, I should tell the rest of the hive, comes back to the hive and lets them know. Bees let them know this by literally headbutting the other bee off the dance floor. It's a very clear signal. So when they headbutt the other bee off the dance floor, the rest of the observer bees nearby all know to update that information. That food source is no longer a possibility. They should not go there. But what about the other bees that have already flown off to the pollen? Well, they're not eventually consistent. So they're still on their way to that plant to find out that there's no pollen left. But that's okay, because it's only a couple of bees. And in the long run, they'll find out, come back, and update their data source in their brain to know that, oh, there's no food there anymore. I shouldn't go back. So they're eventually consistent and highly available, which is what we want for these solutions. It's not perfect, but there are tools we can use to help. This is far more representative of how we work in life. So there are tools that we can help improve the consistency, and one of those is sharding. So sharding is a form of database partitioning where we can separate out very large databases into smaller, faster, more manageable parts called data shards. So a shard basically just means a small part of a whole. So basically just splitting up the database. So it's meant to make very large databases more manageable. So it basically increases parallelism without collisions. So let's look at bees again. So imagine, instead of having all the tiny little cells you find in honeycomb, instead the hive is this one big cohesive cell. And only one bee at a time can fill that up. If I've got one bee at a time filling up that cell or hive, again, I'm going to get a queue of bees trying to fill it up. And that's an issue, because they're wasted resources or wasting time. If we split up that one big cell into lots of little cells, like honeycomb, then we'd be able to have multiple bees coming in, filling different cells within the honeycomb, and not one bee would be blocked. So bees already exhibit this behavior. And so sharding allows us to have this greater parallelism without the collisions and have reduced contention, which means that we can increase our consistency. So we've got another tool here called Backpressure. So Backpressure is a form of feedback or flow control. So without feedback, a distributed system can easily become unstable and it can fail. Any component that cannot support the worst possible case of loading the system can become a bottleneck. So that's what we don't want. We do not want a bottleneck. So let's imagine with the bees, we've got a shortage of cells to fill up with nectar, but we've got tons of honey to put in. We've got a lack of communication and a lack of flow control between those collecting the honey and those making the honeycomb, which there are specific bees for. So what we need is, if this is a case of the publisher is not able to keep up with it's faster than the subscriber. So we got the subscriber here and the publisher here. So let's say that the collector bees are the publishers. They're coming in delivering honey. They're delivering those messages. Now the subscribers are the guys here making the honeycomb. They can't keep up with that demand. So they need to try and get either more resources to come and build more honeycomb, or B, slow down that rate that the workers are coming back at. So they need to have back pressure where they have a form of communication to let the flow know they can't keep up anymore and there's going to be a bottleneck. There's going to be an issue, and it's going to cause wasted resources, potential problems, and potential failure of the system. So bees, again, already do this. They already exhibit this behavior. They're already able to communicate with other bees that they need more workers to come and build honeycomb, or they need to slow down the rate at which they're collecting pollen because they already filled up all the hive. So we need that in our applications. The opposite way round you can think of is sort of a tool called bulkheading. So where the last example was we were looking at when the subscriber couldn't keep up with the publisher, this way round we're looking at, okay, we want the publisher to limit it to the subscribers. So that's when the publisher knows that the subscriber might not be able to keep up. So bulkheading used to be a term used in industry in sort of container ships, and it used to be the case of partitioning the ship into segments at the bottom. So at the bottom of the ship, you'd partition it, so if one filled up with water, it wouldn't fill up the whole ship, and the ship wouldn't sink. That's kind of why the Titanic sunk. So not good to have one big container. So these sections, this idea of bulkheading was taken into software and applied to segregate out resources. So it's all about protecting limited resources from being exhausted. So in the case of the bee dancer that I showed you, let's say this pollen, it's only one flower, right? There's only so many bees that can go and get pollen from that flower. If I send 1 million bees to that flower, I'm probably wasting 9,900 of them. But by limiting it in their dances, bees can communicate just how rich that food source is so that they know how many bees to send. So that they know how to efficiently sort of separate out the bees to the different food sources so they're not wasting any resources. And again, this is exactly what we want from our applications. We don't want to be wasting resources. We want to be able to have some form of communication to protect limited resources from being exhausted, like the flower, because we also want it to spring back afterwards and produce more pollen for future use. So this is all to do with resiliency and responsiveness. Another tool that we use for looking at protecting resources and helping them recover is circuit breaking. Now, circuit breaking in bees is slightly different to the way we do it in software because bees are intelligent beings, and unfortunately, our software isn't yet. So I'm kind of going to show you this example, but bear in mind it is an intelligent being. So when bees get sick, they're actually able to identify that they're not performing very well and that there's something wrong with them. And they sacrifice themselves to be able to for the benefit of the hive, essentially. So what they do is they take themselves away from the hive and isolate themselves. Now that either leads, unfortunately, to death of the bee, or in the pleasant situation, the bee gets better and is able to rejoin the hive. But that means that they don't spread the disease throughout the rest of the application, and they don't waste any resources. So in order to protect resources in software, it's sort of a level above. So you have parental actors who can find out the health and whether their children actors are healthy or not, just like the bee. And if there is not a healthy application and it's blocking some sort of request, then they can take that out of the system and replace it with a new actor or reroute round that actor and wait for it to get better. So it basically gives them a chance to recover. So circuit breakers tend to be opened when a particular type of error occurs multiple times in a short space of time. So that open circuit breaker means that it gets routed around that particular actor and gives it the time it needs to recover itself so it can be used again in the future. And they usually close after a certain amount of time, given enough space. But this is all about resiliency. So they need to be resilient and allow for those failures and have actors in place and methods in place to work around those failures so that we don't get blockages. So how do I even achieve all of these behaviors? I've talked about a ton of tools here, and they're not specific to reactive applications, but they are used to kind of get the behaviors of the reactive manifesto into our applications. But how do I even get there? So there are tons of reactive frameworks out there for use if you did want to have a go. These are actually mostly open source, so I use Lightbends. So Jonas Bonner, the guy who I mentioned who created the Reactive Manifesto, is the founder of this company, and we have a partnership with them as IBM. So they are in charge of Akka, Play, and Lagom. So they're the ones I tend to use. But Microprofile is just releasing, or has released, reactive streams in their latest one. You've got RX Java, Spring Reactor, and Vertex. These are all frameworks that you can use to achieve reactive applications. To varying degrees, some are more end-to-end than others. Some go right from the database all the way through. Lightbends does, for example, others don't. But these, if you're interested, are some of the frameworks you can look up and have a go with if you did want to have a go with reactive applications. So what does this mean in real life? Let's take a look at why we even care. Why are you even in this talk? So let's look at a real-world example of where someone has implemented reactive applications and had a real difference, and it's made an impact. So let's look at Verizon. So Verizon are a customer of our Lightbend IBM collaboration, hence why I'm using their stats, and I'm allowed to. But they have an application where they usually get about 175 million visits per month. So it's a very popular site. They get 88% of their interactions are digital. So most people order their phones through this application. And 48% of the digital sales are on their mobile devices. So having an application that is responsive and resilient is really important. Now, what Verizon used to have is a monolithic application, And in their kind of transformation over, not only did they go into reactive application, they also switched to microservices. So some of this is, some of the facts that you'll see and the figures are because they switched from a monolithic to a microservice, but it's also because they switched to reactive. So just bear that in mind. But before they switched, when they used to release a new phone deal, for example, so when the latest iPhone came out, their system just couldn't cope with the increased load. And what that meant was they had to switch off parts of their application. They literally had to shut down services on their application to even deal with the amount of influx of customers wanting the new phone. That's just not feasible in nowadays society. Like, you can't not have parts of your application working. And Verizon kind of realized this and sort of set out to try and solve this. It's a common problem that many people have seen. So, for example, there have been a couple of cases where low performance has had an actual impact, a negative impact on business goals. So the BBC, for example, found that for every additional second their site took to load, they lost 10% of users. That's just a second. And then DoubleClick by Google found that 53% of mobile sites were abandoned if the page took longer than 3 seconds to load. So if they can't deal with an increased load because of increased amounts of users or increased requests to the system, then they're going to lose sales, they're going to lose users. And there have been a couple of case studies where people have seen the opposite. So, for example, Pinterest were able to increase their signups by 15% when they reduced their wait times by 40%. So you can see there, by reducing the amount of time it takes to load and get new pages and get new information, they're able to increase their users, which has business effects to their business. Cook also increased their conversions by 7%, and they're able to decrease bounce rates by 7% as well, when they reduced their average page time by 14.2 seconds. That's not that long, and it made a huge impact to their business results. So what happened when Verizon switched over? Well, Verizon were able to get a conversion rate up by 1.6%. They were able to use an eighth of the infrastructure that they previously used. So not only did it have an impact on sales and how many sales they're able to put through, it had an impact on how much infrastructure they were using and the cost of that. It also had an impact on the developers that they were getting to develop this application. Developers were suddenly 20 to 40% more productive than they used to be. That's a huge increase. Imagine what they can now do with that time. They can now innovate more around their application. They were also able to get their order completion rate down. So that meant that users were happier using their service and came back for more. And their page response time, as I said before, is insanely important, as proven by the tons of case studies that are out there. And this page response time decreased from 7 to 10 seconds to 2 to 3. That's a huge decrease when you think about the milliseconds in that. So they were able to get their application down, and they actually had business impact on this. So their profits went up, and their customer experience had a more positive outlook. But why should you even care? You're not Verizon. Why do you care? So our applications aren't perfect at the moment. I think we all know that. So how can we make them better? Well, the behaviors that I've shown from bees and the behaviors that I've shown from the Reactive manifesto show that actually we want these behaviors in our applications. We want to be able to have these behaviors. So why not try out the reactive application architecture if they're going to achieve these behaviors, the exact behaviors that we want? So if we want our applications to be more reactive, resilient, elastic, we want to be able to have non-blocking messages, maybe check out the reactive application architecture, because I think it's the future of application architecture for these reasons. So what can you do? Well, there are a bunch of resources online. My next slide will take you to some of the links. So if you want to take a picture of that, that's fine. The slides will be up online later. So we've got a ton of resources specifically on IBM, but there are loads of blog posts out there about why you might want to use certain reactive frameworks over others, why you even want to switch to reactive in the first place. So we've just released a new blog series taking you from how do I go from a microservice application to a microservice application that's based on reactive architecture. So that was written by a company called Red Elastic, but it's on the IBM developer site, and that takes you through step by step how to reach that end goal from a microservice architecture. So if you did want to have a go doing it, it will take you through step by step the different tools that I was talking about. So how to add event sourcing in, how to add CQRS in, etc., etc. That does take it through in a nice, easy step-by-step. There's also a ton of, there's a completion course you can do, so there's online learning and badges you can do to increase your understanding of what the reactive application architecture is, and there's tons of videos. So these are some of the links that you can get to. I've also put in things like the Reactive manifesto, so if my diagram or bee pictures weren't clear enough, you can go and have a look yourself. There's also the O'Reilly, so why would you even want to go reactive? There's a whole book on it. There's books on, and there's also the why you'd want to go reactive and understanding it in less than 12 minutes. So those who are really pushed for time, there's just 12 minutes and you should understand it if this talk hasn't already. So then you've also got things like Akka and Lagom. So there's some of the open source frameworks that I referenced. And you got a link at the bottom to the CAP theorem. So for anyone who wasn't familiar with that, it was a bit too long to put in this talk. But if you did want to go away and check out what the CAP theorem is, so looking at availability versus consistency, then check out the CAP theorem. It is some quite interesting learning. But that's pretty much the end of my talk. I finished slightly early, sorry, but I'll be taking questions. And for those who ask questions, I have bees to give away to tempt you. So does anyone have any questions? And as I said, if you want to get in contact and ask me more about this, then feel free to do so. But yeah, any questions? Yes. Yeah. You know what? For that question, I will give it to you. Right, I'm going to try and chuck it, so you're going to have to try and catch. I mean, almost. Right, anyone else have a different question? You can't ask the same question twice. I'm going to put that rule in now. Any other questions? Yeah. Did you draw the bees yourself? They're actually my mom's, yeah. Roped her into it, did a bit of ironing. Was like, if you do one, yeah. So she draws all my bees for me. Yeah. I swear her talent is wasted. Oh yeah, I'll give you a bee though. Yeah, at the back I think. I saw your hand go up first. Yeah. Oh, sorry. Yeah. Mm-hmm. So Akka, Logom, and Play are all part of the Lightbend stack. They're designed to do different things. So Play is more around web frameworks. Akka is more around like the actual Akka microservices, and Lagom builds on top. So if you check out, there's like a really nice diagram which shows you sort of a hierarchy. So it has all sort of Akka and Play on an equal playing field. So you can use both in collaboration. So Akka more the back end, Play more the front end. And there's sort of, there's Lagom underneath it and a couple of others. So there's like things like the Reactive console that you can use. And it will show you how they all link together. But they're used for different things. So if you wanted to do more front-end reactive, then Play is probably the best way to go. Back-end, I would say Akka and Lagom together. In general, people will use Lagom with one or the other, or maybe both. So for example, the Verizon example I showed uses Play and Lagom, but they don't necessarily use Akka. And they've been using the Reactive console, which is Lightbend's paid-for platform where you can monitor your applications, like the clusters and things like that, and when they redo it. But yeah, there are other frameworks. I don't know as much about them because I don't work with them. So there's like RxJava. I try to be quite neutral with my slides so that you're not limited to just what I know. But there are some out there. For those who are interested in which framework they should choose, there is a talk online by my colleague Mary Grigelsky. Email me or tweet me if you want which one it is, and I can send you the link. And she did it at DevNexus earlier this year, and it goes through why you'd want each one. Cool. No worries. Yeah, so your hand up.
Sorry, suppose we have two microservices and we have data sync problem between them.
Mm-hmm.
Does reactive architecture suggest some solutions?
Yeah, so that's more around the tools we use within the reactive application architecture. So for those who didn't hear, I didn't get your name. What's your name? Anna. So Anna asked, what if you had two microservice and you had a data sync problem between the two? Does reactive architecture have a solution for that, essentially? That's more around what frameworks you use within the reactive application architecture. So for example, if the whole CQRS event sourcing that I was talking about, where you have different read and writes, that often has a data sync problem, as I was saying, because it's eventually consistent. So it depends on whether you've implemented sharding alongside that. and how you've implemented, like whether you're using event sourcing or whether you're just using a normal database. Are you using event logging? With event logging, it's quite easy to get up to date because it's just like following a set of instructions. Because you're saving the state rather than the data, it's really easy to go back to a previous state and then just follow the instructions again to get to the current state. So that's why I sort of recommend using event streaming or event sourcing logging. Loads of different people call it different things. But it really depends on what tools you're using within your application architecture, because not everyone uses all of them. Yeah. No worries. I feel like I owe a couple Bs. Sorry. I should keep up with this. I need an assistant. Could one of you pass that back to the gentleman back there for me? Please don't steal my B. Thank you. Anna, here's yours. Anyone else got questions? Yeah.
What kind of real-time issues did you face while implementing these, or did it just work out of the box, all the resiliency?
I mean, nothing works out the box. So there are obviously issues that you've got to go through. So, for example, if you're going to switch from a database form to event streaming, there are obviously issues with re-architecturing that because you're doing a completely different type of data source. And again, with CQRS, if you're having separate reads and writes, there's obviously teething issues with separating out those databases and getting them to be consistent, as consistent as you can make them. In the blog that I mentioned, it's like a blog series. So I think we've released 1 to 6, and there should be 8 coming out. That takes you through each step by step and kind of leads you by the hand through them, if that makes sense. And that I found really useful for going through to understand like where my problems were in comparison. But I think mostly it was around, for me, the data and making it as consistent as I could and switching that data over. The rest of it I found relatively straightforward and simple. The frameworks are really easy the ones that I was using for me are really easy because it does all the clustering automatically and it's able to self-allocate leaders. So the way that Akka works is it's like lots of actors they call it actors instead of microservices, and the actors form clusters and each cluster performs a service. So within that service, if one actor goes down, it's fine because there's like 3 other actors to perform those tasks. And they self-nominate a leader to basically sort of monitor the actors within that cluster. And that's all part of Akka's framework. Like you don't actually have to code or implement any of that. It's done for you. So in that regard, that was fairly easy, I found.
Follow-up question?
Yes, yeah.
We are using a database,
Mm-hmm.
and we are going to event sourcing architecture.
Yep.
So that will definitely work. And is it better?
I can't say it will definitely work. I probably need to see what you were doing. I personally think that event sourcing is better. There's like a ton of blogs online which will probably argue either way. We do have an event sourcing offering which I don't work on, but I do use sometimes for our applications. So I can get you in contact with them and they can help you through if you'd like some help with it. Yeah, if you want to contact me with my contact details, that's fine. Yeah, cool. Yes, sir.
Just asking about what level of application would it be
Yeah.
applying to? I mean, you talk about online applications and number of users, but
Mhm.
what's the kind of, I guess, is there a level or is there a kind of like point where you wouldn't need it and a point where you go above a number of users to require it?
Yeah, I think for sure. So if anyone didn't hear the question, it was, is there a sort of a level of users or size of the application, I guess, in which you'd want to implement something like reactive architecture compared to just normal microservice? And yeah, I definitely think that's the case. I think if you've got a really simple application, realistically, if I've got a really, really, really basic one-class application, I'm probably not even going to go microservice application architecture. So there is always a cutoff point. It's not always best to use something like a microservice or reactive for that reason. I think once you're getting into the microservice sort of region, when you're starting to use that sort of framework and that architecture, it's worth looking at reactive just because you're still using, so as I was saying with Akka, you're still using this concept of bounded context, but in this case it's an actor instead of a microservice. But you're adding increased reliability and resiliency by having multiple forms of those. Now, obviously depends because having multiple of the same service obviously adds an increase in cost. So that is something to bear in mind, whether you have that capability and you're able to sort of afford that and architect for that. But that's sort of a personal choice depending on your application and your cost. But I think once you're looking at microservices, that's when you want to start looking, okay, do I need the resiliency? Do I need the responsiveness? Can I make it lighter and quicker without it? Probably sure, yeah. But do I need it for my customers? Are they expecting this from my application? For people like Verizon, where they have millions of users, yeah. If it's my own like photo website where I'm storing my photos, I probably don't care because it's just me. So I think it depends on the context of the application and sort of whether you're going microservice architecture already. Yeah, but if you've got follow-up questions, feel free to like email me with them. Yeah.
So how are you going to achieve that we have high load on some particular endpoint and the rest of low load services can have
Sorry, I'm slightly deaf. Could you say the question again but louder? Thanks.
You gave the example where when Hive under attack, they recruit workers from inside.
Mm-hmm.
So how we can achieve in this system
Yep.
when we have high load on some particular
Mhm.
endpoint and then other can help to
Yeah. So that's all part of the framework. So the ACCA framework, for example. So in ACCA, as well as being able to self-nominate leaders, they're also able to self-reorganize, I guess would be the word, the different actors. So if I've got a service, let's say I've got a restaurant, and I've got loads of people trying to book a table and no one paying for some reason. My food's all free. So I want to reallocate my resources that I've put, so the pods or actors or clusters that I've got waiting for the payment service, and reallocate them to the, let's say, book a table service. That's part of the framework. It's able to identify that you've got wasted resource over there and reallocate it to areas that you might have increased load. So, for example, the book a table. So it's not necessarily in the way that you program the application. It depends on which framework you use. So in like Ben's, obviously I know about that, but I don't know about the others. Yeah. Cool. Let me get a B. Are there any other questions? Yeah.
What do you think about the future of circuit breaking? Because I know that Netflix stopped contributing to the sticks. We use it on production and it's really useful, especially for latency management.
Yeah.
But I think the contribution or the alternative is not too many.
I mean, I guess we'd have a conversation outside. It's probably a long conversation around that. So the question was around the lack of contribution to circuit breaker specifications. And yeah, we can have a conversation outside. If you want to come find me in the IBM booth, we can have a conversation around that. But I'll give you a B anyway. Any other questions whilst I'm here? I've got like 4 minutes remaining. Sorry, I finished a bit early. I was quick. Anything else? No, silence. Oh, we have some, yeah. You have to speak up a bit, sorry.
Sorry. So it's about duplicate transactions. How can you ensure that we don't have duplicate transactions and also we don't have different states of the transactions in different parts of the application?
So you're talking about more data storage in terms of those transactions? I guess it depends on how you've architected your data. So whether you're doing storage of data or storage of the state of the application, right? So if you're doing storage of the state of the application, you shouldn't be storing any data in the first place because the data is sort of within the state, if that makes sense. So when the transaction comes through, that should be a new event and that should be added to the event log. So that's the next item in the sequence of events, for example. So there shouldn't ever be a time when you've got both. So therefore, there shouldn't ever be a time where one's trying to overwrite the other, for example. Does that make sense? I hope that's answered your question. If not, you can come and speak to me. Yeah, I can imagine. Databases always are. If you want to come and speak to me outside and I can have a look at the application and stuff and maybe talk to you a bit more in detail about it. Yeah? Perfect. Cool. Anything else? Silence? No? Good. Cool. Well, thank you very much for coming.